Hi everybody, Miss Brown here. I'm going to be doing some work down here. I'll hopefully make this a little bit bigger so you can see it. So some things you're going to need for this, we're going to talk about delta G, learn how to do some calculations with it. So you will need this handy dandy pink sheet and a green reference sheet. We're going to learn some new equations, but let's just kick it off with something we already know. We're talking standard entropy change, and you need to calculate it for this classic equation of N2O4 becoming 2NO2. So this is our products minus reactants, just like we did with delta H. So if you haven't done an ed puzzle in a while, it will stop in just a second and give you a chance to put in your answer for this question, and then I'll talk about it. Okay, so here's what I got. I summed the products. We've got 2 moles, right? And make sure you're looking at these units up here. It's going to be something interesting. So the units of standard molar entropy are joules per mole Kelvin. Okay, and so since I multiplied these by their molar quantities, I got 2 moles of NO2 minus 1 mole of N2O4. Those are their standard molar entropies. So I got 271.2 joules per Kelvin. Okay, so we're going to start off with entropy because it's going to come into this idea of Gibbs free energy that we talked about last time I saw you. So enthalpy and entropy are both contributing to spontaneity. We used to just think that it was all about being exothermic, but then we found out that if you increased entropy, that was part of it too. So these two things are both in the direction of having free energy, being able to be done spontaneously. Okay. And so what this dude Gibbs was able to do, trying to move this out of the way. So what this dude Gibbs was able to do was he came up with a new state function, Gibbs free energy. Yeah, very subtle. And it is G. So G is the Gibbs free energy. It's really hard to calculate G, so almost everything we're going to do is going to be change in G, delta G. It's thought of as the available energy to do work for us. So if something is exothermic and increases entropy, the amount that it will go without us doing anything, the amount of energy it will give out to us is basically that delta G, that free energy. It is different than enthalpy, however, because we have entropy coming into play here. The sign of delta G tells us if the reaction is spontaneous or not. So what we're going to see with delta G is that if it is less than 0, if it is negative, if you have a negative delta G, that is spontaneous. If your delta G is exactly 0, the reaction will be at equilibrium. If delta G is positive, and we're talking in the forward direction because we are going to bring some equilibrium in here, then it is non-spontaneous. So anytime something happens spontaneously and we don't change temperature and pressure, we know that the free energy is always going to decrease because that free energy is going towards doing that action. Okay, so calculating delta G is actually not too tough. We've already seen lots of things like this. So we can use delta or our tables. So just like our pink table, go ahead and take yours out right now and look at it. And we're going to use this delta G of formation, just like we've used, delta S and delta H. So if we look here, delta G of formation for looks like some manganese oxide right here, manganese 4 oxide is negative 465.1. Now that's in kilojoules per mole. So pay special attention. These two are both in kilojoules. This is in joules. So that's going to get interesting. Okay. So if you would look at your green sheet, we're going to see some interesting things here. No, sorry. Go back. We won't get to that yet. So standard free energy of formation, so these numbers, just like standard enthalpies of formation, these delta H's, the free energies of elements in their standard states are set at 0. We kind of just decided to do that. So just as a reminder, when we're talking about pure solids or pure liquids, they're always just the pure, nothing dissolved in it. The standard state of gas, right? Because we have this little naught symbol up here, meaning that this is at the standard state. So we're at 1 atmosphere of pressure. If you're talking about a solution, it's 1 molar. Okay. And if we're talking about an element, delta G of formation is going to be 0 at its standard state. So now we can pull out our green sheet. Sorry, I jumped ahead of myself. And we can see here, there is our delta S. There's our delta H. There's our delta G. They're all the same. You sum the products, multiply them by their molar amounts. You sum the reactants, you subtract them, you get an answer just like we see here. Very straightforward. So let's calculate one here. Okay, we're going to use delta G formation data to calculate the standard free energy change for this reaction. We have P4 plus 6Cl2 making 4PCl3 at 298 K. So let's calculate for the forward and then let's calculate for the reverse. Go ahead and get that done. Great. So I hope you got the same answers I did. Let's make this bigger so you can see my work. Okay, so what I've done here is I took my product, the PCl3, we have 4 moles. I multiplied by our negative 269.6, and then I summed my reactants. So we have an delta G of 24.4 down here for the P4. And then this is Cl2, which is an element in its standard state. So that ends up being 0. So I got negative 1,102.8 kilojoules. Okay. If we were to reverse this, right? So what ends up happening is this goes over here, right? And then this ends up getting subtracted. We're actually just going to flip the sign. So hopefully you remember that pattern back from enthalpy. Our delta G is going to work the same way if you do forward and reverse. Okay, so how do we use delta G? Why do we care? Well, it will tell us if something is spontaneous or not. So that's huge. So it's how we account for this battle between entropy and enthalpy like we saw in the POGIL. Sometimes things happen, sometimes they don't. It depends upon temperature. And sometimes you won't be given all these delta G values. So we need to figure out how to settle this fight between entropy, enthalpy, and at what temperature these things happen. So we already know that things that are exothermic, right, that have a negative delta H, right? Those things tend to happen. We also know things that increase in entropy, things that have a positive delta S tend to be spontaneous. So let's figure out which one wins with a very easy equation. So this one is awesome. I think it might be my favorite. I don't know. It just is beautiful. So if we're at thermo, over here on our green sheet, you can see it's right there. They have theirs as standard. We're also going to talk about non-standard, but there you go. I just wanted you to see that right there. Okay, so here's what we have. The delta G, the change in free energy, is equal to the change in enthalpy minus temperature times delta S. So the other way we calculate delta G is what we just did here. We found the delta G's of formation into the products minus reactants, but sometimes you aren't given that information and we will need to use this up here. So let's just process some questions for delta G equals delta H minus T delta S. So I just want you to go ahead and answer these in the Edpuzzle in just a second. So which one is enthalpy? Which one is entropy? What does a positive value correspond to? So for what values of delta H and delta S will delta G always be positive? Okay. Yeah, actually, I'm going to cut this and go back because this slide sucks. So let's just see how we're doing here with this equation. Let's process it conceptually. So what I want you to do is answer these in the Edpuzzle. So you can read those, get them in there, and then we'll talk about them. Okay, so now let's see how you did. So what is enthalpy? It's delta H. Entropy is delta S. What does a positive value for enthalpy correspond to? Corresponds to being exothermic, right? And that will contribute to delta G being positive. So if delta H is positive, it makes delta G more positive, less free energy, less spontaneous. So the more endothermic you are, the less spontaneous you are. Okay, what does a positive value for entropy correspond to? It means increasing entropy, means you're going with the tendency of the universe. And look at how we're subtracting this term here, this T times delta S. So the greater your entropy change, positive entropy change, the more negative this term will be. The more negative, the more spontaneous you're making delta G. Okay, a negative value for enthalpy means that you will be exothermic. A negative value for entropy means that you will be reducing the entropy, fighting the universe, making delta G more positive. So when is delta G always positive? Well, if you have an endothermic and a decrease in entropy, right? It will be positive because this is a negative sign. If your delta S is negative, it makes this positive. This is positive. Delta G will always be positive. When is it always negative? Well, if you have an exothermic reaction that's releasing energy, this term will be negative. If delta S is positive, we'll be subtracting this positive, so that will be negative. Delta G will always be negative. And this is the big thing we have to worry about. The units of enthalpy, if we look at our sheet here, are kilojoules per mole, or just kilojoules. And then the units of delta S are joules per Kelvin. So we're going to take care of that when we multiply it by T. Remember, this T always needs to be in Kelvin, and you will either need to convert your enthalpy value into joules or your entropy value into kilojoules. Typically, delta G is in kilojoules, so you will usually convert entropy into kilojoules. So get used to that calculation. Okay, so let's just do one. Let's calculate delta G for the formation of nitrogen monoxide from nitrogen and oxygen gas at 298 Kelvin, given that the enthalpy of formation, the delta H standard state is 180.7 kilojoules, delta S is 24.7. So do that and see for a bonus point if you can tell me if the reaction is spontaneous or not under these conditions. So here's how I did this. I took the 180.7 kilojoules, that's my enthalpy term. I subtracted 298 Kelvin, multiplied by my entropy, which I converted to kilojoules. The Kelvin cancels. So this was about a 7. And then I subtracted that, so I got a positive 173.3 kilojoules is equal to our delta G. And since it is positive, this is a non-spontaneous reaction. So let's look at this one without looking up any data. Predict whether delta G for this reaction is more negative or less negative than delta H. So I want you to do some qualitative stuff here. So take a second and look at this. Answer that question. Okay, so the way I'm thinking about this is our delta S term positive or negative? If our delta S is increasing entropy, if it's positive, when we subtract it, it will make delta G more negative. So these are all gaseous, so we're really going to go by number of moles. Oh, we do have some liquid. Oh, interesting. So we should compare really our moles of gas. So we have 6 moles of gas on the reactant side, only 4 moles of gas, or only 3 moles of gas on the right-hand side. So I'm going to say that this looks like it's going to be a decrease in entropy, which will make this term right here end up adding to delta G, so it will be less negative. Let's actually calculate delta G and find out if this is spontaneous or not. Oh, and a hint for this question, you are going to have to calculate delta S to get that term. So let's check out my work here. I calculated delta S using our standard molar entropies. So 4 moles of water, 3 moles of carbon dioxide, those are our products, minus the sum of 1 mole of our propane, C3H8, and 5 moles of O2. Don't forget that O2, the enthalpy is 0, the delta G is 0, but entropy is only 0 at absolute 0. So make sure you look up that number. Okay. So what I like to do for my brain is I like to find these different sums so that I'm not confusing the subtraction here. So I found that my overall delta S was negative 374.9 joules per Kelvin. And that actually connects with what we already figured out. We're making a liquid out of a gas. We have more moles of gas as the reactant. So having a decrease in entropy makes sense. Okay. So then I used my equation up here that we love. So I have my enthalpy term here. I'm then subtracting my temperature multiplied by my, and I forgot to change the units there, multiplied by my entropy. And look, I converted it from joules into my kilojoules so that these could subtract. And I got negative 2,108.3. So it looks like the enthalpy still 1, and this is spontaneous because of that sign, and pretty spontaneous. That's a pretty big number. Okay, so y'all are doing great. So let's talk about changing temperature and what is going to be going on here. Okay, so let's just work through 1 and 2 together. So for the Haber process, so remember our Haber process is this. It's our N2 plus 3H2 yields our 2NH3. Okay, so we're going to see that our enthalpy is negative 92.38. Our entropy is negative 198.3. Assume that enthalpy and entropy do not change with temp. They do, but we're just going to make an assumption. So let's predict the direction in which delta G for the reaction changes with increasing temperature. Okay, so I'm going to help you through the thought for this, and then you're going to answer the question. So is it endo or exothermic? Enthalpy is negative, so we are going to be exothermic. So that's not going to do anything. We're just going to let that be for temperature right now. Now this delta S term, okay, negative 198.3, we are decreasing in entropy. We're going to end up subtracting that negative number. So as temperature, as this number gets bigger, what happens to this whole term and what effect is it going to have on delta G? So think about it for a second. If we increase temperature, what will happen to delta G? Will it become more positive or more negative? Yeah, good job. I hope you said it will be more positive. So then we can calculate delta G at 25 degrees and 500 degrees. And, I just think for terms of time, this is a long Edpuzzle. Let's not do it. But if you do it, you end up getting what we decided. Okay. So let's check this reaction out. I think this is going to be a good problem for you to end off and make sure that you got this. Okay, so let's answer some of these questions on our own or together, and then I'll have you do C and D. So first things first, look at the enthalpy values, look at the entropy value. Is the reaction exo or endothermic? I hope you said exo. We've got that negative sign there. Does the reaction lead to an increase or a decrease in the number of possible microstates of the system? So look at the entropy. What's happening to it? Looks like a decrease, right? That negative sign means that we are decreasing the entropy. We're decreasing the possible number of microstates. That is getting reduced. Okay, so what I want you to do now is calculate this standard delta G for the reaction at 298K. Okay, so what I got here is I converted my entropy again into kilojoules, and so it was negative 35.4 kilojoules, and then if we're subtracting a negative, it's plus 25.479 kilojoules. I got negative 9.921 kilojoules, and that is going to be spontaneous. Okay. So this is just a great slide. We will review this when we talk, but hopefully out of this, you got the idea that if it's exothermic, we're increasing the entropy of the universe. This is going to be spontaneous. It's going to happen. We will always get a delta G that is negative. If we have an endothermic reaction that also decreases the entropy of our system, it will never be spontaneous. Delta G will always be positive. So then where we have some interesting things happen is when they disagree, and the temperature will win out here. So if you are exothermic, but you decrease the entropy of a system at low temperature, right? Because temperature is multiplied by delta S. At low temperature, this term will matter less. Being exothermic, producing heat into a colder environment will be more spontaneous. Once you start upping that temperature, this term over here will take precedent and we will get a positive value for delta G. The opposite is true for an endothermic. So if you are changing if you're taking in energy, but you are increasing the entropy of your universe, then when the temperature is low, we won't be spontaneous, right? But when it is high, we will. Okay, so what is next for delta G? You are going to start thinking about delta G at equilibrium. That is what the POGIL is for. When I see you after spring break, we will practice this and clean it up, but I want you to make sure that you are checking the key up at the front podium, helping each other. Let me know what you need, and you can put any questions in here you want to ask me.